think we can start.
Sure. Okay, so today I'm going to talk about a project with David Hume and Romain Tessera. Okay, so Benjamini, Schramm and Timar a few years ago came up with quite an intriguing invariant for graphs or groups called the separation profile, and it's got some nice properties. It's monotone under coarse embeddings. So, for example, subgroups. It doesn't worry about distortion, so it can give you some invariance in that direction. It's a coarse invariance in the sense, so it's well defined for a finely generated group. You don't have to worry about choice of generating set or anything like that. And with David and Romain, we're thinking about some examples to see what kind of behavior this could have, and using that to give some abstractions for coarse embeddings of groups. So what I'll do today is I'll tell you a bit about this separation, how it naturally leads to generalizations. If you'd like, the separation is a sort of p equals 1 case, so something that could equally well be defined for any p, connected to Poincaré inequalities, and some interesting examples where we've worked out what these things are. So that's the plan. It's 10 o'clock in the morning, so if you want me to explain anything more or go slower, let me know. Okay, so first, separation. Okay, so all graphs are bounded degree. So suppose we have a finite graph gamma. Then we can define the cut size of gamma to be the minimum size of a subset S. So this is number of vertices. So S is a subset of the vertices of gamma, with the property that all connected components of gamma minus S have size at most half of the size of gamma. So for a finite graph, how many vertices do you have to delete so that all the pieces are at most half the size? For example, if you delete half the vertices, that would suffice, but often you can do a lot better than that. And if you have an infinite graph, or potentially infinite graph, the separation profile of x is the function which is defined by, for a given value r, it's the worst case scenario of these cut sizes. Okay. So, given all the subgraphs of the most r vertices, which of them, what's the maximum value of the cut? So, examples. Suppose x is a tree. Just make it regular tree. Then this is 1 always. There's a not completely obvious step in that proof. Okay, it's kind of reasonably obvious. So on the one hand, there are two directions here. First, you have to show that, well, first you have to delete at least that one vertex to have, if you have a connected graph, to have components that are less than that in size. And the other way around, if you have any subgraph of a tree, you can find a vertex so that when you delete that vertex, all the pieces left have at most half the, just sort of move into the middle, that'll work. Say we take the usual Cayley graph for Z2, then this is going to be basically like square root of R. And again, this is not, I'd say this is, the fact that it is this is immediately believable. Proving it is, again, there's two directions. So on the one hand, you take this box, it's believable, and you can prove that you need roughly the side length of the box, so there's R vertices, to chop it in half. And if you have any subgraph whatsoever, then you can find a cut set of that size. It'll work. Okay. Some properties. So, what's what we're talking about here? For functions f and g, we'll say that f is less than or equal to g. Means kind of game function type comparison. Okay, so if you have a regular map, for example, a fuzzy symmetry, so what I mean by regular is Lipschitz, and I'm not going to force it to be a coarse embedding, although that would work. I'm going to say that the pre-image of points has a uniform bound of how many points are in it. So they can be very far away from each other, but the number is small. So if you have a regular map from x to y, then the separation of x is a lower bound to the separation of y. How does that work? Well, this tells you that you can lift back cut sets at most with a multiplicative increase in how big they are. That's basically the proof. Examples of such maps.
What does the Lipschitz have to do with that statement?
You want that.
Oh, I'm sorry. Oh, there's the parameter. Okay.
So you need F to be Lipschitz as well as have the preimage, so that things that are connected in X are roughly connected in Y. So, for example, if F is a coarse embedding, or even more specifically, a quasi-symmetry. So in this case, if X is quasi-isometric to Y, then the two separations are comparable. Okay. So for coarse embeddings, you could think, subgroups. Then separation of H is lower bound for the separation of G. So it doesn't care about large scale distortion. It only cares about chopping things into pieces, and doesn't care about if you have a very distorted subgroup, as long as it's a subgroup, so it's embedded. Of course, okay. So some more examples. So this was introduced by, I said, Benjamini, Schramm and Timar. I suppose I should put that down somewhere. But this kind of question is obviously fairly classical. It's got connections to Cheever constants, which we'll come to in a minute. And the result that they cite as an inspiration is a result of Lipton and Tarjan from 79. So if X is a planar graph, then the separation profile is at most square root of R. So this is a very particular case of very much more general phenomenon. So they didn't phrase this in terms of separation. They were giving results for all planar graphs, but subgraphs of planar graphs and planar graphs. So it gives this consequence for the separation profile. Let's get more straightforward. So as of their paper, I think this is the list of what was known. So we said trees, we said Z2, so ZD. Like R to the D minus 1 over D. Again, boxes are your optimally bad situation, where the cut size is the site of a box with R vertices is R to the 1 over D, and the size of a hyperplane cutting in half is this big. This is so if we have hyperbolic space, we get two cases. So
hyperbolic space isn't a graph.
okay,
Just.
so this is
I'm just saying.
this is a good point. Despite it not being a graph, Benjamini, Schramm and Timar just talk about it and say, if you like, take a graph approximation and you'll be fine.
Okay.
It's quite something very. We in our paper we do completely define things for metric measure spaces and proves things about moving to discrete approximations, and I'm going to do my best to say none of that in this talk.
Okay.
It's extra machine. So if you see a space that doesn't look like a graph, you can either imagine the analogous definition, or you can just take a graph approximation. And in this case, what we get is R to the D minus 2 over D minus 1. If D is at least 3. Well, the lower bound is clear because you have spheres or horoballs, say, if you prefer, which look like Z to the D minus 1 in here. So you're at least that big, but in fact that's the worst case. So if you like spheres here cause the problem, and if D equals 2, you have log R. And here's not spheres, the sphere is a circle, which is constant separation, but balls with diameters are the worst case. Okay. And they also had the separation of a product of trees is R over log R. So that, we think, was the different kinds of separation functions that turned up what they did. Okay. Now, how else to think about this? Proposition. Okay, let's define this is kind of a Cheeger constant that's comparable to the usual Cheeger constant to be the h1 of gamma, to be, again, gamma is a finite graph. Then phi of the gradient, the one norm of gradients over f minus its average, the one norm of that, where f is a function from the vertices of gamma to R, which is non-constant. Okay, some things to define there. Okay, so the average value of f is f gamma, and puts the gradient, well, it's more the norm of the gradient. It's just the variation in the ball around gamma, or ball around x. You can define this a couple of ways. I'll do it this way. Okay, so that's a quantity. Knowing this value gives you a Poincaré inequality on your graph, because if you know this for all functions, you can say if this, this is greater than or equal to 100. That tells you that the one norm is the deviation of the function from its average is controlled by 100 times the gradient of the function. And this is comparable to what you might be more familiar with, the usual Cheeger constant. So David used this observation when he was looking at expanders in graphs. So he showed them that the separation is sublinear if and only if you don't contain an expander, it's a subgraph. Anyway, so that's not a proposition, that's a definition. So the proposition is that this is here's another way to calculate the separation. Okay, so the separation can also be defined as the sup of h1 of gamma times the size of gamma. There's a non-trivial step in that relation here. Clearly, if you have a set with some good cut sets, then you can define a function that's 0 on one side, 1 on the other, and it'll have small gradient. So one way is fine. The issue is that the cut size and the Cheeger constant aren't obviously related. You can have a hard to cut graph with a little bubble off the side, which is so this has small Cheeger constant, but large cut size. But if you chop off any kind of obviously bad bits, you're left with a fat bit in the middle that's also about as hard to. This Cheeger constant is large and has, so that this is like the cut size of the original graph. Okay, why 1? So why not do other p? And so that's one thing that comes from looking at this definition. The other is it gives you a connection to Poincaré inequalities, and we know a lot about Poincaré inequalities. For example, boundaries of hyperbolic groups. Nice ones of Poincaré inequalities. And so our two goals were to see what happens when you think about different Poincaré inequalities, different p's, and to use some of the things we know about Poincaré inequalities to say things about even the usual separation profile for groups where it hadn't been obvious how to calculate it. Okay, so let's talk about this. So we just define HP gamma for P between 1 and, well, we can put infinity if we like, to be the exact same thing, except we do P norm. Okay, and then we can define the Poincaré profile to be the soup of overall subgraphs of psi equals to R. Okay. So why do this? Well, a couple of properties, just off the bat. Again, we have that if there exists regular map from X to Y, you get lower bounds from the one for Y from coming from the one for X. So it gives you coarse invariance. It's called monotone coarse invariance of finitely generated groups. In other words, if one group coarsely embeds into another, then for any particular p you care to look at, you get this order preserving property. There aren't so many of those. There's asymptotic dimension. There's the growth function. And then there's work of Pierre recently, which is in many cases another way to get some of the results that I'll state later. Which says sort of LP cohomological dimension on the left will be less than or equal to the formal dimension of the hyperbolic group on the right. Infinity. Infinity is basically another way of talking about the growth of the group. So we've already said that lambda 1 is the separation. Basically, the infinity profile is just the inverse of the growth, R over the inverse of the growth. So you divide R by the minimum k so that there exists some ball in X with size, k with number of vertices at least R. All right. The first, well, what would you think about first? One thing, we've got Poincaré inequalities here. if you have a group of polynomial growth, nilpotent group, then there are lots of classical Poincaré inequalities for balls on those groups, and that gives you a lower bound, which we show is also an upper bound. So G is firstly nilpotent, and its growth function is like r to the b. Then for any p its Poincaré profile is comparable to r to the b minus 1 over b. So there's no p dependence appears. One thing I should also mention for properties is you don't need to prove this for all p. You just need to check 1 and infinity, because if 1 is less than or equal to p less than or equal to q less than infinity, then lambda p x is lower bound for lambda q x. Although this comparison depends on p and q, but you can work through the definitions to figure that one out. Okay, so far so not terribly interesting. But there are two statements in there. One of them is roughly coming from classical Poincaré inequalities on balls and nilpotent groups. I should say this is also true for compactly generated locally compact groups with the right definitions. The upper bound for any subset at all, you have to find something that's no worse than you would see on the ball, a suitable function. So that you have to find suitable decompositions and use the fact that this is finite stochastic dimension to split it into pieces where you can build functions and uncontrolled sets. But what I want to spend the rest of the time talking about are hyperbolic groups. Before going on to that, any questions so far? Okay, so hyperbolic groups, for example, the free group. So if we have a tree, then we calculate the P profile. So here we know the constant case is 1. Sorry, the P equals 1 case is a constant. P equals infinity case is going to be r over log r because of exponential growth. And what we get in between is r to the p minus 1 over p so as p increases, we see things that are worse and worse. Now, how do you prove things like that? Again, you have to prove some sort of Poincaré inequality, in this case, on a ball in the tree, and you also have to find suitable functions in any subsets of trees. There's suitable functions in subsets of trees is easy. You can find something in the middle, 0 one side, 1 other. Proving the Poincaré inequality in a ball is a bit fiddly to get exactly the right behavior. You basically do the fundamental theorem of calculus and lots of Holder's inequality. So between any 2 points, you have, let me take a step back. The argument's inspired by some ways to deal with G or constants for trees. And there are computer science people who've thought about all this kind of stuff for ages, where you can compare the tree to the complete graph by Cheeger constant in the tree to the Cheeger constant in the complete graph by for any two vertices in the tree going along the unique embedded path between the two, and the difference between the two values here is going to be a sum along the path. And if you do suitable weighted polar inequalities, you get this kind of estimate. That was probably too cryptic to be helpful, but how do you prove Poincaré inequalities at all? I guess this will come up in all situations. Generally, you have to have a good family of paths that spreads out. So if you want to prove a classical Poincaré inequality with the actual gradient and Rn, one way to do it is between any 2 points. You don't just do the fundamental theorem of calculus along the line. You do the fundamental theorem of calculus along the whole family of spread out paths. And the fact that they spread out gives you a way to show that the gradient has to be large along quite a good amount of the space. If this is small and this is big, then the gradient has to be big on some reasonable amount of space in between. So that's how you do a Poincaré inequality. And the issue is Poincaré inequalities aren't true for trees because space doesn't spread out, it all goes through a point. But how badly it's not true depends on how much it's squeezing through a point. And so that's the kind of thing that we're estimating with these Poincaré profiles. And how bad things are is measured differently for different p's. Anyway, once you've got this, you've got some consequences. If we have any hyperbolic group, okay, not elementary, then it has embedded trees. Okay, so that gives you a lower bound. So, for example, if we think about the profile of, let's just do H3, let's do a cartoon. We've got two lower bounds now. We have the lower bound from so let's think of this as the power. So we've got a lower bound of r to the alpha, so we have let's ignore infinity. We have a lower bound of a half for all p, and we have this lower bound of p minus 1 to the p. And these are two lower bounds. And we see that for this kind of lower bound, and this is nearly sharp. So this I find interesting because the minimizers, or the sets that you need to look at for different values of p are different. So when p is small, we have the spheres. When p is big, we have r to the p minus 1 over p, or r log r. So trees work here. And then at exactly the sharp exponent, we have r to the d minus 2 over d minus 1 times an extra log term. This is coming from balls. So you see this generalizes the result of Benjamini, Schramm and Timar for H2. For H2, you get log R, and for D bigger than 2, you get this. So this is showing that really what they were detecting was the coincidental behavior at the at this sharp dimension d minus 1. Yeah.
So as P gets large, it's more and more like growth and less like separation.
Yeah.
So that's why you're.
Yeah. Exactly. It's giving you a kind of spectrum in between. And this is where the two things are exactly matched. Okay, so how did you prove this? Well, we've already discussed the tree thing briefly. For balls, you do exactly, it may or may not be new, but we couldn't find it anywhere. So we proved a Poincaré inequality on the ball. There's a couple of approaches for P less than d minus 1. We have embedded z to d minus 1s, but you can do a more analytic approach where you look at the boundary at infinity of the group. And we have Poincaré inequalities on the boundary in an infinitesimal sense. And you can control functions on the boundary, and you can push that inside to give control on discrete spheres in a way that you control the constants as the spheres get bigger and bigger. And that gives you this, but this also works for any time you have a hyperbolic group with a Poincaré inequality on the boundary. So for example, if we take the boundary at infinity of HDK, where K is RCHO, real complex quaternion, then we have Poincaré inequalities on the boundary. I guess Jerison. Okay. So these are Q-regular metric spaces where Q is the Hausdorff dimension of the boundary, and Q equals 1, 2, 4, or 8. I think. So for example, and in this case you get a lower bound of R to the Q minus 1 over Q. So for example, if you complex hyperbolic space, not to get too lost in the woods, the boundary infinity of this is a 2D minus 1 dimensional sphere, but its Hausdorff dimension is 2D. And so rather than having the 2D minus 2 over 2D minus 1, we get this 2D minus 1 over 2D. So this gives you that there is no coarse embedding of HKC into H2KR, for example. That's definitely true for quasi-asymmetric embeddings. You can do conformal dimension of the boundary. But trying to prove that for coarse embeddings, there's now this new wave of PRs with large-scale conformal maps. But that's non-trivial. And of course, it's not just coarse, it's regular maps where you're allowed some bounded amount of folding. upper bounds, there's this paper of
You have to keep
I don't know if I should
Just
take
stick your
that.
arm up there, yeah, that'll work.
Take it as a bit of a hint. Well, it's good to have a kind of disco atmosphere. So there's this paper of which this goes back to how Benjamini.
Oh, no. Let go. You can lift it up, yeah.
Jonathan, did you work out the profile for complex hyperbolic space?
No, we just have
Just the band?
these lower bounds.
Okay.
So this is the upper bound.
Mhm.
Well, we didn't also do the ball. The motivation for the ball was we had the upper bound, so figured out Poincaré inequality. So for the upper bound, we use a variation. So there's this paper by Miller, Thurston, Favarsis, and someone else I've forgotten about center points of graphs and circle packings and things. And how do you do an upper bound? You have to cut everything. So you have some subsets. You want to find some point which is in all the half spaces that cut it in a reasonable way. So you do this with the Helly's theorem argument and the fact that the space is finite dimensional. And then at this point, you look in all the different direct ways you can cut with half spaces through this point, and you find one that's no worse than average. And then you can define a function that's 0 here, 1 here, and Lipschitz in the boundary, and you can push it inside, and you get a way to calculate the gradient norm by using the Lipschitz bound and the growth of the space. And depending on what P is, different factors win when you're doing these sums. If P is larger than the growth of the space, then you get the Dirichlet function. If it's smaller, then the worst case is when everything is pushed as close to the center, so that the Lipschitz, so that the change is as big as possible. If you have points that are quite far out, when you push in a Lipschitz function, the change is not so big compared to when they're in the center. So you get a sum that's an inequality that's optimized when things are squashed as close to the center as possible. Okay, so that's a bit hand-wavy. We don't have this for complex hyperbolic space, but we do have it for Bourdon Pajot buildings. So if we have S at least 5 and T at least 3, we can define a group GST is with S generators of order T, which commute with their neighbors. So this acts on a Fuchsian building where you've got right-angled S-sided polygons with branching of order T. These are hyperbolic. They have asymptotic dimension 2, and they're two-dimensional. Round infinity is a Menger sponge. They have a Poincaré inequality so there's a QST where Q is some, ST is some number, regular metric on the boundary infinity of this thing with a Poincaré inequality. Okay, that's properties, and then what do we get? Again, we get, so this Poincaré inequality in the boundary pushes into spheres, so that if P is less than this dimension, which is like D minus 1 for real hyperbolic spaces, you get R to the Q minus 1 over Q. Well, you have this for all powers, but this is where it's sharp. And otherwise, the trees take over, the growth takes over. Okay.
What is Q?
Q, ST.
No, Q is T, but this one, which is R to the power Q minus
Sorry.
R.
Now, what's interesting here is QST is 1 plus log Q minus 1 over R cosh Q minus 2 over 2. It's in 1 infinity, and it's a dense set of values. So this gives you, if we just think about P equals 1, this gives you a dense set of exponents so you get a dense set of exponents possible for the separation. So for example, we get lots of groups who have the same growth exponential, the same asymptotic dimension 2, but for alpha less than beta, G alpha does not coarsely embed into G beta.
Can you, so QST is a function of S and T.
Oh,
Can
sorry.
you say what is Q and
Sorry.
T?
I was trying to avoid
T minus
no
1.
clash, but my memory is
T minus
T and S. Thanks.
P and Q, they.
Usually people use P and Q, but we've got too many letters going on. As T gets bigger, you have more branching, the conformal dimension goes up. As S gets bigger, sort of things are spread out more, and the conformal dimension goes down. Another consequence, if you want, for any K, there exists some alpha naught such that for alpha bigger than alpha naught, G alpha, which is a hyperbolic asymptotic dimension 2 group, doesn't coarsely embed into real hyperbolic three-dimensional space. So you can find groups that are in some sense small that can embed into even coarsely. So quasi-asymmetrically all this is known because you can use boundary geometry, but coarsely until I think the paper of Pierre last autumn, there wasn't another way known to how you do this. It'd be natural to try and see what you can say for other rank 1 symmetric spaces. The issue is we couldn't find enough. Oh, well, how do we prove this? It's a similar, we have an estimate at the dimension, but it's not sharp. There's this lower bound and this times log upper bound. So this again is spheres and trees for the lower bound. For the upper bound, we use Halley's theorem again, and we use the wall structure of the building to find sort of center of any subsets, which can be controlled cuts around that subset. And we don't know enough complex hyperbolic geometry, or at least I don't, to get enough enough walls in complex hyperbolic space. So that's why we didn't prove that case. It seems interesting though that this is another way to somehow detect, for hyperbolic groups at least, the conformal dimension of the boundary in a coarsely invariant way. So yeah, thanks very much.
What for other saying two-dimensional hyperbolic buildings? So do you
Yeah.
use essentially that it's like right angled?
We just use wall structure.
Okay, so wall structure.
So
So this is essential, right? Because it looked like you said about the boundary, because the boundary doesn't matter what is the two-dimensional hyperbolic building, the boundary is Menger curve in any case.
yeah, so you have some sort of a priori band on how many walls are next to, say, 3 polygons. Or let's do 2 polygons. Or an edge. Everything next to a face is joining an edge. You have some a priori band on how many of those there are. And you consider all hyperplanes, or all half spaces, with respect to walls, for which 99.9% of your strange subset is inside the half space. And then using Halley's theorem, for the suitable parameters, you get that the intersection of all of these is not empty. And using that very priori bound, you get that it has to have diameter at most 2. And when you figure out all that same, it's giving you a way to find not one half space, not one wall, but 2 walls, which have a fair amount of your set on either side. And then you can do this Lipschitz extension of boundary functions. So if you have enough walls, you're good. The problem is if you try and apply Halley's theorem without doing it carefully, if you only have certain nice walls that you understand, when you intersect everything, you don't really have control on how big the intersection of all these half spaces is. You need enough half spaces so that you can chop your space every way that you want to, but you need your half spaces to be convex so that you can do this kind of boundary interpolation functions inside. So yeah, pick a group, and it's probably not been calculated. Okay, one-plated groups, it's n over log n. If you have a finely presented group, separation is either constant if it's virtually free, or at least logarithmic. We don't know if there's a gap for finely generated groups. Yeah, lots of questions.
So getting upper bounds seems to be harder than getting lower bounds.
Yeah, they're very different flavor. So lower bounds is you find the right subset and you prove a Poincaré inequality in this fairly well-established machine of you find suitable curve families that spread out enough. For example, for the hyperbolic balls, you can kind of send some of your paths, but not too many through the center. So I didn't see that in the literature anywhere, but it wasn't so bad. For upper bounds, you need to deal with all subsets, and they're more working hands-on. There isn't so much of a machine. What machine there is seems to be find a center, find a cut through the center that's good. But you have to deal with all possible subsets, because if you have some coarse embedding, you don't know where your balls have gone. They could have got all kind of crazily distorted.